Dear scientists, doctoral candidates and students, dear colleagues, it's a great honor and pleasure for me to welcome you to the 12th International Excellence Talk of Karlsruhe Institute of Technology, KIT, also on behalf of Thomas Hirt, our Vice President for Transfer and International Affairs. This lecture series was initiated in May last year, and it is designed to provide a platform to discuss the current research topics of internationally renowned scientists in an interdisciplinary context. And that actually is why KIT established the International Excellence Grants and Fellowships Program, which makes it possible for researchers at KIT to invite outstanding scientists from abroad to perform joint research. Meanwhile, we have already initiated 6 nomination rounds for International Excellence Fellowships and invited over 30 extraordinary scientists from abroad for a research stay at KIT. And today, I'm very happy to introduce Kamran Behdinan, Professor of Mechanical Engineering at the Department of Mechanical and Industrial Engineering, University of Toronto in Canada. A warm welcome to our today's speaker. He's an international authority on multidisciplinary engineering design, especially in the field of multi-scale analysis and design of multifunctional lightweight structures. Professor Behdinan is the past president of the Canadian Society of Mechanical Engineering. He also is board member of the Canadian Engineering Qualification Board for Engineers in Canada. And he has received many prestigious national and international awards and recognitions. We are very honored to host you, Professor Behdinan, at KIT as an International Excellence Fellow. His research stay in June and July is part of his collaboration with a scientific group of Professor Albert Albers from the Institute of Product Engineering, IPEK, of KIT. Dear Professor Behdinan, I'm looking very much forward to your talk today. The screen is yours.
I would like to thank the International Office for giving me the opportunity to introduce, highlight of my research, an overview of the work that we have been doing at the Advanced Research Lab for Multifunctional Lightweight Structure at the University of Toronto with my research team. I am going to practically talk about some of the research that we are doing in this category of applications. As was mentioned, I'm the founding director of this institute, and I do have other roles in terms of the multidisciplinary design and innovation, which is all funded through the National Science Engineering Research Council of Canada. With that, I would like to start by making some comments about what we do in this lab. The lab is specialized in testing and simulation and optimization of new multifunctional lightweight design solution for automotive, aerospace, and biomedical and nuclear applications. The team that are under my supervision working in the lab includes currently 2 postdoctoral fellows, 11 PhDs, and 3 masters. But over the years, we have many great graduate students who did research in this field, and many of them right now either are faculty members or are working in industry. Quite a remarkable achievement by this group of people. And we do 2 kinds of research. One is on the fundamental research, which I'm going to introduce, and some of the work is on the applied research. On the applied research, we collaborate with several industrial companies and partners and institutes. So as you can see from this very overview of what we do, you can see that we get involved with multidisciplinary design optimization of complex systems. We do testing of them, and we characterize the modeling of these structures at the nanoscale microscale, mesoscale, and macroscale. We do quite a bit of a testing of different components of these systems. And we also get involved with characterizing and designing of smart structures and sandwich structures. Because the work is also involved in the lightweight, nowadays, with the advancement in additive manufacturing process and other intelligent manufacturing process, we get involved into the process of characterizing, understanding, and designing of these components. Some of the work is involved with printing them, printing different sensors, and modeling them. So the lab is equipped with, these are some samples of the equipment we use for testing. So we have all sorts of shakers, data acquisition systems, and systems to be able to make them. And then also we use various machines to be able to test them on the high cycle fatigue, on the static testing, and so on. We do have a different frequency, like for example, this piezo shaker, which can go very high on a low payload. And we, of course, will monitor the results through various scanning and probe system to be able to better understand their behavior. So these are some of the work that we do in the lab in terms of experimentation for component testing. So we do set it up and we conduct. Some of these components are coming from industry and getting them from the clients. Now I'm going to start by going to a few examples of the research, but my focus is going to be today also to introduce some new concepts in the multidisciplinary design optimization, how that integrates into the operation of the design and analysis and characterization of lightweight structure. The project that you see is sponsored by National Science Engineering Research Council of Canada and is an industry project with the client and aero engine manufacturing. Initially, they asked us to look into how we can reduce the vibration of this engine and better understand that. This project, as you can see, started back in 2014. And even today, we are working on certain aspects of this work because of the importance and some of the testing facilities that we were able to develop. And that's very relevant to the current design of the new engines. So one of the initial work that we have done on that was to characterize this journal bearing, which is, we call it a squeeze field damper. These are the main support of these rotors, aero engine rotors. So we have done that. This is a very complex system. And the speed of this can go all the way to 20,000 RPM. And at that level, with this thin film of the oil, lots of physics is happening in that area. The overall thing is that how to characterize them, what are the damping forces, and how we can make it better. We see a lot of physical phenomena over there at that very high speed, the effect of the inertia on and the performance of this journal bearing, squeeze field damper, we call it SFD. The cavitation that can come at that speed, and sometimes even we notice some spikes in the pressure, which was coming from the fluid ruptures. So the system is completely very complex nonlinear system. And when you bring at that speed the effect of the temperature, then the viscosity change, and physically it's a very challenging problem. In terms of the modeling, of course, people, they come and they do some approximation at the support for the damping and the stiffness. And they start to, but the numbers that they get is normally from some experimental testing. But when we get to that level and we want to get more accurate solution out of that, we do need a very sophisticated test rig for that. which we designed that in collaboration with the industry partners. And this is a conceptual design of that. This test rig was designed back in 2016, 2017. The calibration of that took us a long time. There are so many sensors involved with the way that we collect the data from the temperature, from the pressure, proximity, and the displacement. So it's a very sophisticated test rig, and it can go all the way to 20,000 RPM to characterize the squeeze film damper. This is the one that right now is in use to better understand of the new generation of the aero engines that are the manufacturer designing. Of course, we look into the overall, again, performance of this, and we look into all the key parameters that are important for design of this squeeze film damper and how they perform. But the project was initially not about the squeeze film damper. It was about also the aero engine model, how the vibration is happening in this very complex system. Assume that a simple engine may have 15 casings, and these casings are around the rotor, and rotor is built inside that, and then with all the support. And these casings are connected to bolted flange and through certain connections over there. Overall, the system is vibrating, and the connections are passing the load through the casings. And these are all nonlinear effects. And there are so many features built into these casings. So modeling of that requires a sophisticated simulation to be able to better understand how the vibration is transferred among the, from the rotor to the casing and how it goes to all the way to the pylons. So for that, there was analysis of that casing was critical to understand the transmission path of the load all the way to pylons of the aircraft. So that's the source of vibration. And on the aircraft is one of the key sources of vibration in the aircraft, among the other two. So practically, we had to use very sophisticated techniques to do this transfer path analysis. And we used techniques like bond graph, and we have a number of publications on that we can review, visit that, and learn how we did that. Going back to the testing of high cycle fatigue, design of the many components in aircraft, automotive, and so on relies on that. So we need to build a fixture, we need a shaker, we need to properly gauge them and properly monitor the dynamic response of these components. And what's the use of that? Of course, when we go through the vibration analysis of them, when we characterize them, then it comes back to, we can look into the failure analysis of that, we can look into fatigue analysis of that, and we can start to also build some model based on that, and then use these things to in the loop of a design to be able to properly design this. Assume that you are designing a rotor blade, which is a very complex geometry. So that's the use of this testing, that hand in hand with simulation comes to be able to design these complex components. So we can see that this is a very crude flow of the way that these things can be handled. So started by the testing and going to the loop of the multidisciplinary optimization. And that multidisciplinary, what are these disciplines? Of course, we can talk about the structure here, manufacturing, fatigue life, computational fluid dynamics, CFD of that, and of course, cost, and many other things. So ultimately, going to that loop, we can come out of that with the optimum design. The optimization is needed to be able to tune all the parameters of the design, and also to be able to make it lightweight and cost effective, that's why we are directing that in that direction. So I'm going to, this is a textbook definition of the multidisciplinary design optimization. When you have more than one discipline, and these disciplines are interacting with each other, and there are so many variables between these disciplines that are talking to each other, you have to pass some variables to another one disciplines and so on. So this requires a structured way of handling this problem in terms of coming up at the end of the day with the optimized solution that can have a significant effect on the performance of the ultimately these complex systems, like aircraft, like aero engine, like many automotive components, and many other systems in nuclear and so on. So there are so many techniques have been developed over the past many years, and these techniques right now are mature. Initially, we started with self-computing, understanding the optimization method, what are these evolutionary optimization method, but that's now all of the way we use them. There are so many toolboxes around that. If we need to advance them, we advance them, but that's fine. It means that on the optimizer, we are not very much concerned. We are mainly want to get this structure to be able to handle these complex problems. It's not about optimizing how these variables are interacting with each other. What's the sensitivity of these variables? Which one we can dump them that they don't have much effect in the design. So there are so many of these techniques. We can work with functions, and sometimes with complex systems like imaging systems and so on. We can also deal with functional functions. So these are techniques. The easy one is MDF, but there are other techniques. In the lab, we use effectively the collaborative optimization. This is something that is my favorite, but there are other techniques also. So this is, for example, a very simple structure that shows you how these disciplines can be interacted. This MDF, which is a simple version. Disciplines are not directly collide with each other, but parameter from one discipline goes to the other discipline, to the other discipline. Ultimately, you have a global optimizer up there to be able to do the optimization of design. An example, a practical example of that is this wing box. So this wing, when you start to design a wing box, you start with some geometry. Then after that, you don't know this is the ultimate design, but you build a force around that, and you run a CFD to understand the aerodynamic forces on that. With that, that information is passed to a structure mesh now. So that information comes to a finite element to be able to get the structural performance of that, or a structural response to that load. And then ultimately, that load is going to deflect or change the shape of the wing box, and all of that comes back again and go to the initial mesh that we had for the CFD. So we have a aerodynamics discipline and we have a structure discipline. These are very obvious example of the multidisciplinary design optimization. And so many design variables. These things can go all the way to hundreds of design variables back and forth between them. So ultimately, this loop is going to be go around, and ultimately you get a converged solution, which is the actual shape of the wing box. We have tested that on a number of cases. This is one example of that we grabbed this. We got the parameter of 737 wing box, and we just started with the crude geometry. And after that, we went through the loop, and we got a very nice profile of the wing box, all of that, and with all the pressure distribution and so on at different span of the wing. This is a rigid wing. Of course, we can grab the rigid wing and make it flexible and then go up. So even for the flexible wing, this method works. So we worked on that. We apply that to many, many systems. This is just a very simple example, and it's a published example. We use the same technique to design a rotor blade. And as you can see, there is a very MDO loop, the multidisciplinary design optimization loop, that you start from some initial design, we go to the CFD structure. We define all the geometries can be built to the model, all of the variables that those geometry has for the profile of the blade. And then through this loop, you can come up with the shape of the correct shape of the blade, and which has enough structural integrity. And so many codes now, PSO, for example, particle swarm optimization, these codes are available. You can use the modules no longer. This is a complex system. There are some commercial software, but I like to practically use the in-house code to be able to manipulate them to get control of the sensitivity. Some of these variables are not deterministic. Some of them are indeterministic variables. Sometimes you need to use reliability-based optimization, or even sometimes you have to guess the variables. Some of the geometry you have to guess them. So there are more advanced technique on the MDO, which is called possibility-based design optimization. So, and that's good, is very good and effective in derivative designs. This is an example of an automotive car cross beam. They wanted to get this designed properly for a lightweight system, and they give some design variables and some constraints for that. And we started, MDO can easily grab a block of metal and go to the process of topology optimization. And through this process, you can come up at the end of the day with the final design, which can handle the loads. This load can be static load, can be dynamic load, NVH of that, noise, vibration, harshness on this, and also can handle the crash, because the knee boosters are connected over there, and in the crash analysis, we can use that. So these are very interesting components of a car that we were able to design that through this process. And a fundamental research that we have done in the lab was multi-scale modeling of nano, meso, micro, and nano, micro, meso, and macro systems. So we found out that in the damage modeling, most of the work that has been done in the past was using empirical or semi-empirical methods, which cannot represent properly the damage. And practically, the material that involved in some of these composites and these structures are quite coupled and complex. So we better to use a better method to go through the scale to analyze them. And of course, sometimes multiple lengths and times get interacted in the analysis of the systems. And of course, the computational cost was just using MD, molecular dynamics, is a little bit at the atomic level, maybe high, how to come up with a better method. So the method is the question here. And that's the fundamental reason. We started back in 2002, and we are still working on it, on many, many applications, specifically the additive manufacturing. So we developed a concurrent multi-scale method called bridging cell method. It's well published and documented. And the way that the at the nanoscale interacts with the continuum is through a series of matrices that we build to be able to speed up this transition and in terms of the simulation. So that was very successful. We used that for non-indentation, some fatigue analysis, and we applied that to different materials. We applied that to ceramic compounds. So we had successfully applied that to Nextel 720, which is a CMC, and other materials. I don't go to the detail of that, but overall, you can see that the process of evolvement on that. So bridging cell method is now well documented and published, and it is a handshaking between the atomistic side to the continuum base. Now, if we want to go to a little bit to the meso scale, we use other methods like cohesive continuum based method. cohesive methods or DM, dynamic element method. This specifically for Nextel 720 3M, we were able to model that completely and understand the microstructures and the atomistic structures and the interaction with metrics and overall the damage and oxygen vacancies within the material, the structure. These are at the elevated temperature. These are going above 1000 degrees. So it's quite complex to model that with a simple FE, and maybe it's not working that. With that, we did quite a bit of work on the smart structures. Number of papers per year we publish on this with different layer of the sandwich. We can have any type of porous layer or top layers on the piezo and practically properly model them with different carbon nanotube infusion core and composite core, and also different orientation of the structure. We look into transient, heat transfer transient analysis, and we look into dynamic performance of this kind of a structure. We have looked into this structure even with the application to energy harvesting system, and it's the way that these things can be designed for that application. As I mentioned to you, discrete element method have been used, you know, that initially was developed many years ago for powder compaction. And nowadays, people are using that, researchers are using that for different kinds, like we have been using that for ceramic composites. This is an example that I'm showing you regarding the heat transfer and transient response of this kind of a smart structure. Of course, the dynamic response is also on the other side. But that's the work that we have done on smart structure. Moving to lightweight and additive manufacturing, which is going to be the last part of my talk today, is that you are already familiar with the benefits of this manufacturing system. I'm not going to go through that, but I want to mention that there are certain restrictions, and we need to do more to better understand the process and be able to predict that and be able not to go to a trial and error mode. We want to properly model that, the process, and at the end of the day, get the right product out of it. It's a very, very effective method in terms of the development of the lightweight structure. We found out that there are certain things that we can do. One of them is the topology optimization integrated to the process that can help quite a bit to understand the steps that we need to take for this manufacturing of compounds. And there are so many variables that can affect the, for example, for the FDM process, printing process, there are so many variables that can affect the performance of this overall the manufacturing process and the component. And some of them, for example, layer height, printing speed, raster orientation, infill density, and so on. So when we look into the process, we look into all these parameters to see that how we can get a better product out of that and predictable product out of that. And then another aspect of that, of course, is the surface quality and the curing of that system. So it's quite a bit of a work still needs to be done for different materials to be able to use AM effectively for the different components. And there is a good paper here that if someone wants to look at that, is about the effect of the topology optimization in AM. It's very organized paper, and they talked about the topology and the construction and size optimization. I highly recommend you to look at this paper. We do have also some papers. So building, because of the nature of this process and the number of design variables involved, if someone wants to really better understand and design these components, need to go to a loop of the MDO, multidisciplinary design optimizations. And that gives you a better understanding of the process, the interaction with the structure, properties, and the performance of these systems. So for that, I highly recommend to use MDO in this process. We have done some optimization work on that. Still work is ongoing in my lab. I've got a few students, PhD students, working on it currently. And one of the projects that we are developing, a collaborative project with KIT, is on this topic. So this is the way that from one cantilever beam systems, we wanted to see that if I go and make the constraint based on the stress, can I get a better solution of that, the lightweight and higher integrity for that structure? I don't want to lose the structural integrity, like structural stiffness and so on, which we were successful on that. The paper was published back in 2021. So this is quite a bit of a research going on in this domain. Another area that is fascinating is about health monitoring of this structure. So we started, now the health monitoring means that how the structures overall behave during the process and after the process. And in order to understand that, we can use different sensors, contact or non-contactless sensors. We tried the fiber optic sensors, so FPG, and fiber Bragg grating fiber optic sensors. And we did both on the, we insert that, and we laid it up on the process, on the component. We wanted to see that, how that works. Of course, there were certain parameters that we had to consider during the manufacturing, and there's certain procedures that we followed, and we tested that. And we tested the static testing and fatigue testing. So we found out that it's quite interesting that we can, when you embed the sensor inside the, in the process, inside the manufacturing, that gives you less impact on the fatigue life, because anyway, you are adding something to the component, less impact on the fatigue life, and can better predict the statically and fatigue properties of that component, that AM component, as the manufacturing component. This was published about a year ago, and this is an ongoing research that we are doing. Now we are looking in different sensors and different ways of health monitoring of these components. It's good to have that because that helps us to predict the behavior of these components prior to the end results of the component, rather than using the trial and error method. Overall, we believe that AM is the future, and that's nothing new about that. People are working around this. We believe it's going to help a lot with lightweight multifunctional structure. Health monitoring is a great study that should be included in the design of these or assessment of these components. And of course, the effect of the artificial intelligence, machine learning integrated to the intelligent manufacturing process of this component is very, very important. We have done quite a bit of a study on the quality of the surface finish of this component. And that's the place that machine learning or deep learning can be used. There are other research that is going on. We are printing a pressure sensor right now. This is a PhD project happening in my lab with a material group lab outside the University of Toronto. And we are using it to foam, but these are special nanocomposite. We are using PDMS, allometrics, and also TPU, both of them. And then we add the nanoparticle and we look into the overall dispersion of the nanoparticle, the volume fraction, and agglomeration of these particles, and what is the effect on the piezoresistivity, and the mechanical properties of these foams. So it's a smart foam that we are developing. This work is almost complete, and we have a number of publications on that. We have, as I mentioned, we use deep learning and machine learning into understanding of the defects. And we did actually some work on the hotspot detection for silicon wafer. And we use that dimensionality reduction to be able to improve and predict the behavior of some nonlinear mechanical work, like, for example, metal forming. Very complex sheet metal forming, very complex plastic deformation. And we were able to successfully implement the dimensionality reduction to be able to speed up the computational time and not to go to these softwares to run this. So we use different methods of dimensionality reduction, and we submitted 6 journals. 2 of them have been published. One is actually about a few days ago was accepted for publication, so you can look into that. Now, all of the work that I mentioned, you can see the concept of that in this book that was published a year ago in the lab. So the concept of some of the important things that we have done, the foundation of that is published in this Advanced Multifunctional Lightweight Aerostructure book. And with that, thank you very much.
Thank you, Kamran, for your today's talk. Yeah, Professor Behdinan will stay to the end of July at KIT, but you can also address him per email. And you can find his contact address on the web here from the University of Toronto, as you have seen. So thank you very much for being with us today. Thank you, Kamran, for your talk. And I wish everyone a very nice afternoon and evening, and hopefully you can cool down a little bit. So thank you. It was very...
Thank you, everyone. Thank you, class. Elena, all the best to you guys.
Thank you, Kamran.
Good.
Thank you.